Okay, this is Chapter 2, Section 2. Again, the chapter is on atoms, molecules, and ions. And let's go ahead and get started with the second section. We're going to take a look at the evolution of atomic theory in this section. And the outline of what we're going to be taking a look at is as follows. We're going to outline the milestones in the development of modern atomic theory, summarize and interpret the results of J.J. Thomson, experiments of Thomson, Millikan, and Rutherford, and describe the three subatomic particles that compose atoms, and define isotopes and give several examples for different elements. Okay, in this first diagram here, we've got what's called a cathode ray tube. This is an early cathode ray tube, pre-1900s. We'll actually demonstrate one in class via video. That's a little bit more modern, and we used to have them in classrooms, and we don't anymore. I don't know why, but for some reason they've largely become unavailable, and I've actually tried to order them on eBay and Amazon and look all over the internet, and I've not been able to find a single one for sale anywhere. But essentially a cathode ray tube has as you can see here in the diagram is another example of it too, but as you can see here, it's got a high voltage source that's got a cathode, which is a negative charge, and an anode, which is a positive charge. And essentially you're running that high voltage through the cathode into the anode, which is funneling it down to the other end where you have a scale on the outside of the glass. And the example here would be you'd run your voltage through this side here, and you'd have your magnets here, as you can see, and you'd run the electrical power here, and you can kind of see a little bit of the outline here of the scale on the outside of the glass. Now, when we work with a cathode ray tube, one of the neat things about it is it creates this beam of light, which is really energized electrons inside of a gas contained in a vacuum. And so you can see this beam, and it shoots straight across. Now, what happens is you've got these magnets here, and if you were to apply let's say a positive charge on this side, it's going to attract the beam. The beam would normally be going straight through here. You can picture this was supposed to be a straight line. But if you put a positive charge here, you would see the beam bend towards the positive charge. If you put the positive charge on this side, you'd see the beam bend towards the positive side. Okay. Now, what happens if you flip it? What happens if you use a negative charge? If you use a negative charge, the beam moves away. And if you were to put the negative charge on the opposite side here, the beam would move away in like fashion to the other side. So what this really told J.J. Thomson, who worked with this cathode ray tube early on, was based on what they knew of magnetism at that point in time, and as we know it today, if you have two positive charges near each other, they repel. In other words, like charges repel. If we had two negatives, they would repel as well. On the other hand, if you had opposites, remember the opposites attract rule. So if you had a positive on one end and a negative on the other, you'd attract, and vice versa. So what they found here was when this beam was traveling through, when you put a negative charge on one side, it was repelling the electrons away. But if you made it a positive charge, it would attract the electrons. This beam, of course, they didn't know that they were called electrons at this point in time. This is supposed to be attracting. It would be bending up towards the positive charge, which would indicate if it was positive and the light that was traveling through, whatever made up that beam of light, whatever those particles were called, had to be oppositely charged for them to be attracted to the positive and to be repelled by the negative. Quite a simple experiment. And what this showed them was essentially that you've got a particle here, a particle that was negatively charged, and eventually it became known as the electron, or the electric ion. And so they put the two together and they get electron. Okay. Now, Thomson was also able to, based on these, remember you got the scale on the outside, right? So you could see how far it was moving, and he knew how powerful the magnets were. So he was able to calculate this charge to mass ratio. And this becomes very important because if you can calculate the charge to mass ratio, that's the first step in identifying that these particles are subatomic, and also that they're going to play a role in identifying some of the other parts that are yet unknown to them and are going to help with the discovery. The charge and mass are going to help with the discovery of the protons and eventually ultimately the neutrons. So a lot came out of this initial experiment, and it's really a very simple experiment, but it's also a very powerful experiment. And Thomson, through his work, like I had said, with the scale, was able to calculate the charge to mass ratio, and he found that there was a particle that was charged. It was negative, and that it was smaller than an atom. Now, if you remember back to Dalton's postulates from the first section, one of the things were atoms cannot be subdivided. And here we now have something that's smaller than an atom, so a part of an atom. So an atom can be subdivided. So this is the first indication that Dalton might be wrong. Now, another scientist, Millikan, did an oil drop experiment. Sometimes they talk about this and sometimes they don't. They usually at least refer to it. But essentially what he did was he sprayed oil droplets into what this whole thing is called an atomizer. So he sprayed these droplets in here, and they would ultimately fall through this pinhole, these tiny little drops. And as they were falling, he would use this X-ray here to charge the particles. So he would give them a charge as they fell. And then he could also control the charge on these plates, how powerful the charge on the plates were. So essentially he could control between, once he charged these items, with the X-ray, he could control how fast the flow of the droplets were going to move, and he could almost actually make them stop or even go back upwards based on how much electricity he was able to put in. So by tracking how much electricity he was using, and of course knowing the charge to mass ratio of the electron identified by Thomson, he was able to calculate the electrical current of these oil drops. And the interesting thing that he found was that each of these are ratios of 1.6. 1.6, you double that, you get 3.2. You add 1.6 to 3.2, you get 4.8. You add 1.6 to 4.8, you get 6.4. All times 10 to the negative 19th coulombs. C for coulombs. So what he figured out was that there was some consistency here, and it was based on, this value, 1.6 times 10 to the negative 19th, indicating the value of the charge of one electron, and then all of these being multiples of that. So 1 drop, 2 drops, 3 drops with a 4.8, 4 drops with a 6.4. So he was able to figure out that, obviously he was capturing more than 1 or 2 parts when he did this. And so ultimately this becomes a very important experiment because he's able to calculate. Remember, Thomson was able to calculate the charge to mass ratio, but he wasn't able to tell which part was charge and which part was mass. He just had the total value. Now Millikan's able to come and say, well, the charge portion is 1.6 times 10 to the 19th. So now they can figure out the mass of the electron. Because if you know the charge, and you have the charge to mass ratio, if you subtract the charge out of it, the balance has to be the mass. It's just a simple calculation at that point, and that's really the first inkling that the electron is smaller than an atom. Okay, now here you've got the two major ideas that were proposed. So Thomson's saying, okay, so if we have this atom now, we've got parts smaller than an atom, and we know one of those parts that's smaller than an atom is an electron. It's got a negative charge. Well, what's the positive charge doing? How is it acting? So they came up with this idea of this plum pudding. Here's a picture of what plum pudding looks like. Probably not what you would think. From England, and I like to think of it as the chocolate chip cookie model because it looks more like a chocolate chip cookie with positive and negatives, chocolate chips being the negative and the cookie dough being the positive. So you kind of had this this pool, this cookie, with all of this positive charge being the cookie dough, and the chocolate chips being these negatively charged electrons floating around in it. And so this is the model, and it was called the plum pudding model, aka chocolate chip cookie model, that Thomson came up with to explain his results from his cathode ray tube experiment. But there's also a competing idea that comes out by Hantoa Nagaoka from Japan, and this is around 1904, I think, if I remember correctly. And he kind of pictured it like the planet Saturn. If you picture Saturn, you've got this positive core, and you've got these rings around it with things moving around in a circular fashion, and he felt that was like the electrons. And, of course, this was backed up by his observational data that he got from his experiments. He'd been working on this for a while. And while it worked well in most cases, within a few years they were able to disprove this theory. I think even by 1908, I think about 4 years later, even Nagaoka admittedly kind of pulled away from this theory, that it wasn't really representing all the data that was coming out of the experiments that had followed Thomson and Millikan. So nonetheless, the plum pudding model seems to be the precedent at this point in time. Well, so we've got this part that's part of an electron, and part of an atom, an electron, and it's negative. There's got to be something positive to balance it out, because they knew that the overall charge on an atom is zero. There's no charge, right? It's balanced out. So if there's a part that's negative, then there's got to be a part that's positive to equally balance out the negative. And so they go kind of looking for this. And Hans Geiger and Ernst Rutherford and trying to think of the name of the other. There's another scientist that was involved with this early experiment. Of course, Geiger becomes famous for the Geiger counters later on with radioactive material and such. But nonetheless, this was really Rutherford's experiment, and this is probably one of the most famous experiments in physics and in chemistry, called the gold foil experiment. And essentially what they do is they took this radium source, they put it in a metal block of some sort to protect against some of the radioactive material that was being emitted, and they funneled the alpha particles that were being emitted from this radioactive source through a tiny hole, a beam of alpha particles, if you will, right up here. So you've got your radium source being funneled, it's putting out a beam of alpha particles, and it's striking gold foil. If you could picture aluminum foil, you can imagine how thin this gold foil is. It's a very, very thinner than aluminum foil, and it's made purely out of gold. And so the expectation was that when these alpha particles were hitting this gold foil, if Thomson's plum pudding model, remember it was the chocolate chip cookie looking thing here, the plum pudding model with the negative electrons floating around, right, and the cookie dough being the positive. Walk around here a little bit. There we go. And so if you had this effect and you shot these alpha particles at this, okay, and it was set up in this format, then you would expect most all of these atoms to go clear through. These alpha particles, that is, they would shoot right through. They wouldn't hit anything on their way. It's a bad drawing, but maybe you can kind of get the picture. I wouldn't have hit anything. A very bad drawing, I guess, but I wouldn't have hit anything on my way through. And if anything, if there was any deflection, maybe I would have struck something and bounced off a little bit. Okay, so maybe there would have been a little bit of deflection. What they found when they did the experiment, if you look over here to the right, when the alpha particles were coming in, not only did a lot of them go straight through as expected, some of them were deflected, but then some of these actually hit something that was solid enough that they bounced back towards the observer. And this was shocking. This was totally unexpected. They didn't have any concept of this happening at all. And this led to the idea that there must be in an atom, if you picture an atom, rather than it looking like plum pudding or chocolate chip cookie, if you picture a sphere, there had to be something where there was a small, dense nucleus. And so the term nucleus, because this kind of looks like a cell, right? Nucleus comes about. And in this nucleus has to be a positive charge. And they call this the proton. Okay? The proton. So this positively charged nucleus is the result ultimately of the gold foil experiment. So, and what they're able to identify ultimately, if the electron's negatively charged and they know its charge, and they find the proton ultimately has a positive charge and they know its charge, and the charge of the positive charge of the proton and the negative charge of the electron are equal to each other. So if these two are equal to each other, then that should account for everything. Oh, and they knew the mass, right? Remember, they were able to calculate the charge-mass ratio in Millikan's oil drop experiment. He was able to figure out the charge, so they were able to figure out the mass portion of the electron. So ultimately, they're able to calculate out the mass of the proton. But what they find out is, if you add this up, let's call this the mass of the electron. We'll call it like 1/1000th, okay, the mass of an atom. And then the proton's like 1/49th the mass of the atom. Well, this clearly doesn't add up to the total mass of the atom. So if the atom was made of solely a proton and an electron, the total mass, the 149, or excuse me, the 48th, I should call this 48/49ths. Oh, wait. Let's cut this in half. So let's see, 1000th. Let's make this so we're on the same scale with everything. So everybody's looking at it from, so slightly less. So 445 thousandths, 445 thousandths of an atom. So if this is 1/1000th the mass of an atom, and this is 445 thousandths the mass of an atom, you put them together, you get 446 thousandths the mass of an atom. That doesn't add up to the total mass of an atom. So while the positive and the negative charges balanced each other out perfectly, the mass did not. The mass only added up to about half, or slightly less than half, approximately half the mass of an atom. So there's still something missing. What's accounting for that other half the mass? Where is it? And hence they go looking for something. So if this takes care of the positive and negative charges, and we know the overall charge is 0, we need to find something that's got 0 charge, and it's roughly half the mass of an atom. And so they go looking for something that's got that characteristic, and that is going to be the identification of the neutron. And we'll talk about that more in class, but hope this video helped you, and we'll clarify things that you may have questions about this week in class. Thank you.